Hello, and welcome to the next webinar in my series on C++ Standard Template Library by example. Today, at long last, we're going to start talking about the real meat of the Standard Template Library, beginning with its focus on containers, which are one of the key themes, one of the key components that's in STL, along with algorithms, iterators, and functors. So without any further ado, let's go ahead and get started. And I will begin by sharing my screen. So if we take a look here, let's go ahead and start with where the code is. As always, you can go to my repository, C++ GitHub account, and we go to STL, and we're going to go ahead and now go into the S-03 folder, and we'll begin with what's in 3.1. So I'll show my IDE. So what's in the 3.1 is not really code, it's just an overview of containers and STL. And containers are an attempt to try to, or not an attempt, a very successful way of being able to work around some of the limitations with native built-in types, things like C++ built-in arrays, which are very limited. There's a number of things that containers all share in common, irrespective of what kind of container they are. All the containers have the ability to copy their values rather than maintaining references to the values. So you'll see that this concept of value semantics is very common with STL. You can, of course, have containers of pointers, but let's ignore that for the time being. So you'll see that when you do these kinds of things, STL and C++ over the years have evolved other features to make value copying and value returning very efficient. And we'll talk about that more later. The classic STL containers, which are basically the sequential containers and associative containers, the ordered associative containers, all have an order. In the case of the sequential containers, which is what we're going to focus on today, the order is just the order that the elements were added to the container. In the case of the associative containers, the order is basically provided by a key, and it's typically ordered by either the less than or greater than operation. Another thing to remember about STL containers is that they assume you know what you're doing. So in particular, if you do something with STL containers, if you put things in that are incorrect, they're often not going to flag that. So it's kind of a garbage in, garbage out scenario. If you give them objects that are full of mistakes and have problems, then you will get them back with the same mistakes and problems. So C++, as a general rule, expects that you know what you're doing. The containers also include some common operations. So for example, they all have various constructors that can be used to support default construction as well as copy construction for types of the same container type. There's also destructors that will free up the resources that were allocated by the container. And you can also initialize containers from ranges of values using iterators. And we'll see later that that's the way that containers can be used to copy between different types of containers. So a vector to a list, or a list to a deck, and so on and so forth. There's also a number of methods that tell you how many elements are in the container. There's basically 3 of them typically. One is size, which is the current number of elements in the container. Another is empty, which is basically just a shorthand for size equals 0. And then there's also something called max size, which is the maximum number of elements that a container can contain. Also, containers have comparison operations, which is something you won't find with built-in arrays. So you can do things like check to see if 2 containers are equal, if 2 containers are not equal, if one container is, quote, less than or equal to the other, or if one container is greater than or equal to another. And so those are basically just like using relational operations that you become accustomed to for other data types like doubles and floats and ints and so on. Something else that all containers have is the ability to be assigned. So you can assign one container the contents of another using the assignment operator. And then there's also something called swap, which is a very efficient way of swapping the contents of 2 containers. Assignment, of course, is used when you want to make a deep copy. Swapping is done when you want to basically exchange pointers or references internally to the containers. And the main reason for using swap is to be able to do things like strong exception safety guarantees, which turn out to be very easy to do once you know the patterns. And we'll talk about the patterns of exception safety probably about the time we get done with the sequential containers. So let's just quickly go through the types of containers that exist in STL, and then we'll get into the sequential container discussion. So there's sequential containers, there's various types of associated containers, associative ordered containers, and unordered associative containers. And then there's also something called adapter containers or container adapters. So let's take a quick tour through the space of containers. I'm not going to dwell on them in any detail at this point. I'm just going to give you a quick overview and show you where you can go to find the implementations which occur in these header files that we're including in this example. So there's something called a vector. That's the first thing we're going to look at today. And that allows you to have linear and contiguous storage, much like a built-in array, but with lots of improvements that are done because it's done as a class, not as a built-in C/C++ array. There's something called a list, which is a doubly linked list of nodes. So you can do certain operations very quickly, like insert things at random points in the list once you've got yourself to that point. There's forward lists, which are singly linked lists. You can only go forward. You can't go forwards and backwards. And then there's something called a deck. And a deck is essentially a double-ended queue. So you can efficiently add elements and remove elements from the end of the deck, as well as from the beginning of the deck. Whereas vectors really can only have elements added efficiently at the end and deleted efficiently from the end. So those are the four common sequential containers. And that's what we're going to talk about in just a moment in more detail. Then there's also a whole pile of associative containers, and these mirror each other. There are ordered associative containers, which are implemented using essentially ordered binary trees, red-black trees, as it turns out in this particular case. And these are broken up into two categories, sets and maps. And each of those categories has an alternative as well. So we have sets and multi-sets and maps and multi-maps. So how do we differentiate between these different containers? So set only has a key and it cannot contain duplicates. A multi-set is only going to contain keys, but you can have duplicates. A map can have key value pairs, or it does have key value pairs, and it cannot have duplicate keys, that is, whereas a multi-map has key value pairs and you can have duplicates. So those are kind of the main way to differentiate the different types of ordered associative containers. And they're ordered because they're ordered by basically the ordering that you get with either the less than operation or the greater than operation. And this is all done using a binary tree. Then there's also a similarly mirrored set of so-called unordered associative containers. And these are all implemented using hash maps, or sorry, hash tables and hash lookups and so on. So they're a little different in terms of the APIs that they provide from the point of view of what kind of operations you can instantiate these various templates with, but they have similar characteristics. So you have unordered map and you have unordered multi-map, and those have key value pairs that are either all unique keys in the case of unordered map, or could be duplicates in the case of unordered multi-map. And then likewise, we have unordered sets and unordered multi-sets. And as you might expect, the unordered sets cannot have duplicates. They're not ordered, they're just hashed. And the unordered multi-sets may contain duplicates, and they also are hashed as well. Your mileage may vary as to whether it's better to use hashing or the ordered operations. And my recommendation is always, always, always to benchmark your code and see which one is working better for you. It's pretty easy to plug and play these things in most cases, so it's not too hard to switch between them. But it is important to determine empirically which one is going to perform the best in any given circumstance. And then finally, we have so-called adapter or adapted containers. And these containers are stack, queue, and priority queue. Now, I think hopefully everybody at this point knows what a stack and a queue are. So a stack is basically going to give you a last in, first out data structure where you can push items onto the top and pop items off the top. And a queue gives you a first in, first out ordering approach where you can, in this case, you can push items to the end of the queue and you can pop items from the front of the queue. So those are all pretty familiar data structures. You've probably learned about them in other classes. And then the final data structure is a priority queue. And a priority queue is a queue that maintains an ordering. And it's ordered by the item of highest priority. And you can determine what that is. And what always happens is whenever you do operations on a priority queue, like you remove the first item, or you remove an item from a priority queue, it's always going to take the item of highest priority. And when you insert an element into a priority queue, it's always going to put it in the right place relative to the priorities of the other operations in the queue. So those are all the main containers that we have in C++ STL. Let me now go ahead and let's take a look at the sequential containers. And let's just open this up. We'll be looking at the other containers later. So sequential containers are just collections of data elements that are placed in some order, usually the order in which the elements were added to the container. The ordering of the elements in a sequential container have nothing to do with their value. It's the order that they were placed in there. So there's operations, for example, like pushback, which just puts it at the end of the other elements that are already there. You can think of them a little bit like an array, a built-in array, but as we'll see, they have lots more cool, clever semantics and lots more cool, clever features. And they're better than simple C and C++ built-in arrays because they have size, member functions that will tell you how many elements they have in them. They give you iterators to the beginning and one past the end. They provide copy constructors and move constructors and assignment operators. You can pass containers, sequential containers by value so the copies are made properly. And then you can also grow and shrink them dynamically. You don't have to be responsible for allocating memory and making copies of the elements and deleting the old memory and so on and so forth. So they're just much more convenient. So again, as we said before, you've got vectors, lists, forward lists, and decks. So those are the various sequential containers. So now let's start to take a look at some examples of sequential containers. And some of these things will be pretty straightforward, I think, and which is good. It's not meant to be super complicated. These containers are very useful, very common, especially vector, which is the one we're going to look at first. So a vector is basically a built-in array, a built-in dynamic array on steroids. And you can define it, of course, to be a vector of whatever type key you want to use. So vector of int, vector of double, vector of character, vector of employee record, or whatnot. And the dynamic array will grow and shrink at the end. So it's always easy to add things to the end and remove things from the end. But if you want to remove things from the front or the middle, then it's got more cost. Internally, this is all done, of course, by dynamically allocating memory. And that's all hidden from you, of course, by the class implementation itself. And you are not responsible in any way, shape, or form for allocating and deallocating memory, although there's some operations that you can use to pre-allocate memory if you know how big your data structures are going to be. So vectors are very, very efficient. They're basically about as efficient as built-in arrays, just more flexible. You can access individual items by their position index, like get me vector sub 0 or vector sub n, as long as n is inside the bounds. You can iterate over the elements in any order, front to back, back to front, random, whatever you want to do. And you can efficiently add and remove elements from the end. And there's just a little bit extra memory to keep track of all the state necessary to do this, but they're really just about as efficient as built-in arrays. So the other thing that you can do is when you push elements into an array, if the array is too small to store the elements, then it'll go ahead and automatically grow and then recopy the elements into the new array and then add the new one at the end. And this turns out to be something that's optimized. And if you don't like the way it works out of the box, you can reserve the amount of memory if you know something about how big you think your data structure usage will be for the vector. So the vector in STL is defined as follows. It's a template, of course, that takes type name T, which is the element that will be used. And it's got something called an allocator. We're not going to talk about allocators right now. We're just going to use the default allocator, which under the hood uses C++ operator new and delete. If you need to take over ownership of allocation, you can, but that's a more specialized use case that we'll talk about later. So let's go ahead and take a look at how you might use vectors. And this will be kind of fun because it's going to show us first how to do things with native C++ built-in arrays. And then we'll talk about how you can do things more effectively with vectors. But you'll see that the way the code looks is very similar. So here's a built-in array. And this particular one, I allocate statically. So I'm going to have an array of 3 elements. And then you can see I go ahead and assign various values to array sub 0, array sub 1, and array sub 2. And you can see how you can use the array subscript operations on both the left-hand side and the right-hand side of the assignment statement. And I don't have to do it like this. I could also do it like this. I could say equal new int and allocate it like that. Oops. So I could also have allocated it dynamically, but of course, if I do that, I have to remember to delete it or put it in some kind of a auto release object like a unique pointer. So let's just keep it like this for now. Once you learn about vectors, I don't think you're ever going to want to use dynamically allocated arrays in C++ anymore, native arrays. So what we can do here is we can go ahead and print the elements. So we're going to print out the elements, array sub 0, array sub 1, array sub 2. We're going to print them out. I think that's all pretty intuitive. I'll run the code in a second so you can see what it does. The next thing I'm going to do is I'm going to go ahead and define a vector. And a vector is like a better built-in array. In this case, we're going to have an array of 3 elements, just like we did with the array. You can see that I can leverage C++'s overloaded subscript operator in order to basically do essentially identical computations that look the same as they do up here for the built-in array. But this array is much more complicated and much more powerful. Not complicated to use, but just more complicated implementation-wise. And it's much more effective and scalable and flexible than the native arrays. However, if we want to work with it much like we would use a built-in array, we can go ahead and iterate through it from I equals 0 to I less than the size of the array and print out each element one at a time. So I think you'll agree that this code is arguably much cleaner than this crazy code up here, which is how you determine the size of a native array. It's kind of a weird little C-style trick. Okay, now let's have some fun and let's go ahead and resize this array, which is set it back to 0. And now we're going to go ahead and push a bunch of elements into it. So this is using a new feature we didn't talk about before. This is using the pushback operation. And what pushback does is it goes ahead and it adds a new element at the end of the current vector. And if it needs to, under the hood, it'll grow the vector by 1 element, or maybe more than 1 element. That's an implementation detail. And then make sure that there's enough room to store that element into the array. And then the last thing we do after we put the values 0 through 6 into our vector, we're going to show another way to print out the elements. So this was the way we did it before using the vector's size method. But now we're going to go ahead and use something called a range-based for loop. Those of you who are familiar with Java and the concept in Java of a for each loop, pretty much the same idea. So what we say here is for int I, where I is updated by all the elements of vector in the order from left to right, from lowest to highest, go ahead and print out the value of I. And I think you'll agree with me that this code here is much preferable to this code. And in fact, if you take a look, the compiler is actually trying to tell you, don't you want to change this into a range-based for loop? And so if you click yes, it'll go ahead and do that transformation for you automatically, which is very cool. So let's go ahead now and see if we can run this code, and we'll see what the results are. Should be obvious results, hopefully. So it's compiling, and you can see here that what we had was basically in the built-in array, we had 7, 10, 17, and that's what got printed out here. Then when we did the equivalent code with a vector, we got the same thing down below. And then when we went ahead and put 0 through 6 into the vector, we get those results. So pretty intuitive, pretty cool. Hopefully that makes good sense. And that's a very straightforward example of using vector. So let's go ahead and turn our attention now to another example of using vector. And I think we're just going to focus on vectors today and see how that takes us. So this example is really just showing how trivial it is in C++ to switch from a vector of ints to a vector of doubles. And we're going to use a couple other little things here. We're showing how you can use pushback. We start out with an empty vector. We push 1.2 and 4.5 into it. We go ahead and make some changes to its values. Now that we've given them initial values, we can read the values and do some changes to them. And then you'll notice down here, we go ahead and we loop through the vector and we print the elements out one at a time. This example illustrates a new feature. I could have said double here, because that's what I've got in my vector. That would be one thing to do. But another thing you can do in C++ is you can use auto instead of having a specific type. And auto basically is just a flag to the compiler to go ahead and deduce the type that's used here. And it can deduce that because it's a vector of doubles, that each element D must be a double. So hopefully that helps to make some sense. So let's go ahead and run the code. And you can see we get the results out that we would expect. So nothing particularly profound in this example, just demonstrating that you can easily switch from a vector of int to a vector of double, and everything else pretty much stays the same. Let's now go on to another example. And this particular example is going to show a couple of interesting features of C++, especially newer versions of C++. First, we're going to show how you can initialize a vector from a built-in array, and that's what we show here. So we have a built-in array with 10 elements in it, and I could actually leave this out there. It wouldn't change the meaning because the compiler can count the number that there are. And then we go down here, and we also have a const char star that says hello world, and you can see that in this particular case we have that's basically a string, a kind of a C-style string, and then we're going to go ahead and initialize vec1 with the array, which is the beginning of the range, and then the array plus 10, which is 1 past the end of the range. So this is basically showing how you can initialize a vector using a native built-in C and C++ array. So that's pretty cool. Then this here is just showing you another way to do it. This is just putting an initializer list directly in line. And you can either surround that with parens like this. So you can either say, I'm passing this into the constructor. That's one way to do it. Or with later versions of C++, you can eliminate the open paren and just simply use the initialization bracket semantics or syntax. Once we've got vec2, we can go ahead and print it out using the range-based for loop and an auto keyword to deduce that it's a vector of ints. And then down here, we do more or less the same thing with strings. I probably should just go ahead and move this down here because it makes more sense there. So now we're going to go ahead and define ourselves this stir, which is a const char star, and we're going to use that to initialize the vec3, much like we had done up here, except this time we're going to use stirlen as opposed to putting a count, so it's a little bit more abstract. And then vec4 shows how you can do the same thing just by giving individual characters. So we're going to have a vector of character. Now, quite frankly, if you want a vector of characters, you probably really want a string, but here at least we show that you could create it using vector semantics if you were so inclined. And once we've got that, we go ahead and print out the contents of vector4, and let's go ahead and run the code. And I think the result should not surprise you because it prints out the contents quite nicely. So that's showing some other interesting aspects of using vectors, in particular, how you can initialize them with native types using ranges, or you can use initializer lists directly. The next thing we're going to look at is yet another example of vector. And this is going to show you a little bit more complicated example. This is really interesting. This is going to show you how to make a two-dimensional vector, or what passes for a two-dimensional vector, by having a vector of vectors. And so then we're going to do some interesting things once we have our vector of vectors. So you can see down here we have vector of int, which we call myvec2d, kind of a strange name. And then we have a vector of int we call 1vec and 2vec, kind of like the cat in the hat, you know, or you know, cat 1 or thing 1 and thing 2, or 1 fish, 2 fish, whatever. We're going to go ahead and add various elements to 1vec. We're going to give it 1, 2, and 3, and then 2vec is going to get 4, 5, and 6. And then we're going to take 1vec and 2vec, and we're going to go ahead and add them to myvec2d. So myvec2d sub 0 will be 1vec, and myvec2d sub 1 will be 2vec. So you can think of this as basically kind of like an array of arrays, or a vector of vectors, almost like a two-dimensional array, but not quite the same implementation. So now that we've got ourselves this myvec2d two-dimensional vector, let's go ahead and do some stuff with it. So the first thing we're going to do is we're going to use iterators, and we're going to talk a lot more about iterators. We're going to use iterators in order to be able to get an iterator to the first of the vectors in our two-element 2D vector. And then while we haven't reached the end of that particular iterator, we're going to go through each element, and then we're going to have a second nested for loop that's going to take the vector, the first vector in the vector of vectors, and get an iterator for it. So the top level for loop is going to iterate through each of the vectors, and then the second nested for loop is going to go ahead and iterate through each element in the nested vector. And all we're doing here is we're just kind of going from beginning to end. You can see here how we're able to use the vector, and I think we can do this a couple different ways. But the bottom line is that what we're doing is we're iterating through these things, and we're finding ourselves doing a dereference of the iterator, which will print out the value at that location. So, you know, first vector sub 0, then 0, 1, 2, then second element, location 0, 1, 2. That's what the star iterator is doing. We're going to talk a lot more about iterators later. This is just introducing you to the concept of iterators. If you're perplexed by iterator syntax, there's an alternative way of doing this using subscript operations. And we show this down here. So down here, we're going to do the same thing, except rather than using iterators, we're going to use indices, I and j, to iterate through every element in our two-dimensional vector. And at every step along the way, we're going to say my vec 2d sub I sub j. So this looks very, very much like working on a multidimensional or a two-dimensional array in C or C++. In fact, the syntax for the part shown here is really identical. And that all works because of the magic of C++ subscript operations, which you can overload, and that's what is going on there. So that's an alternative way to go. Depending on your perspective, it might be cleaner or not than the approach shown up here. But then I'm going to show you the range-based way of doing this. And the range-based way, of course, is, I think, head and shoulders above everything else, because it's really clear what's going on. We're basically saying, take my 2D vector, and for each vector that's the inner vector in the 2D vector, then go ahead and have a range-based for loop that gives me each element in that inner vector, and go ahead and write that out. And of course, these are ints, but I used auto just to let it type deduce. I'm also using const auto ref here, and that's because I don't want to make a copy of the vector that I'm iterating over in the inner loop. I just want a reference to it to avoid the overhead of copying the contents. So let's go ahead and run this program. You'll see it'll go ahead and compile, and the results that we get out of here are a little hard to see with the way I've formatted it. Whoops, but take a look. So you can see using the iterator, these are the results. Using the subscript operator, we get exactly the same results. And then using the range-based for loop, we get the same results. So each of the different approaches gives us exactly the same results. And chances are, if you were to time them, they'd all probably take about the same amount of time to run. So it really comes down to what you're most comfortable with. And for my money, I kind of like the range-based for loop. I find that most intuitive. But you'll see that that's a newer feature added to C++ 11. So if you're stuck using older C++ compilers, which hopefully you're not, you may have to resort to using one of these other approaches. Okay, so that's a pretty interesting example. Now let's go ahead and talk about the last example. I think that'll be the last thing we'll cover for today. This is showing off some other things about vectors. So first, there's some tips for using them effectively and efficiently. You can use the overloaded subscript operator, which will basically be about as fast as using the native subscript operator. It's just adding an index to a starting point, so it's blazingly fast. And the range-based, the subscript operator does not do any type checking. So it assumes you know what you're doing. There's also another operation called at, which does do range checking. Not type checking, range checking. The subscript operator does no range checking, whereas the at operation does range checking. Something else about vectors, they support so-called random access iterators. We haven't talked much about that yet, but we'll learn more about that shortly. It's often faster to insert many elements into a vector in one fell swoop using the range-based copying mechanisms rather than doing them one element at a time, because they can allocate the memory and slide them around more efficiently. And this is a very common data structure. Vector is probably the most common data structure of use in STL. And so it's very effective and very efficient. So let's take a look at a little example here. We're going to create a vector using an initializer list. And then we're going to walk through this. Notice we auto-deduce the type here to be int. And we're going to auto-deduce the type of the iterator, which of course will be vector of iterator. And we're going to go while we haven't reached the end. And every step along the way, we're going to go ahead and say total, which is this value we auto-deduced, plus equal star and iterator. And so what that'll do is the dereference operation goes and looks at the location where the iterator is pointing, finds the value, and then it adds it to the running total. So that's how you could do this using an iterator-like mechanism in conjunction with auto-deduction. I could also have written this more verbosely if I'd wanted to, but why bother? Here's another example where we're going to use a range-based for loop approach as opposed to using an iterator approach. And this again came with C++11, and I prefer this approach, but I'm showing you alternative ways to do it. And this, I think, is much cleaner, much more clear what's going on. And then, of course, because this is STL and there's different ways to do the same sorts of thing, there's another method called accumulate. And accumulate is actually a C++ template library algorithm. And what it does is it's going to go ahead and start at the beginning, go to the end, and it's going to accumulate each of the elements, and the initial value is going to be 0 in this case. And we'll spend a lot more time browsing around through these methods later, but in a nutshell, this is what this method does. You can see what it does is it takes an input iterator as the first argument, which is the iterator from the vector, one past the end called last, which is the last element in the iterator from the vector, and then it takes an initial value. And what it does here is it goes ahead and iterates through this little for loop from first to last, and every step along the way, it goes ahead and adds the dereferenced first iterator's value to the initial value and stores it in the initial value. And it keeps doing this while last is not equal to first, or first is not equal to last. And then when it's all done, it goes ahead and returns init. So that's just showing you how simple a lot of the STL algorithms are. They're very, very simple in many cases. But it's cool because you can write that code without having to do any looping, without having to think at all about, am I iterating too many times and so on. So each of these approaches has their pros and cons. Left to my own devices, for something as simple as this, I might be tempted to go with a range-based for loop. But as we get more interesting examples later, you'll see that accumulate and other STL algorithms are a fantastic way to simplify access to basically containers. And they always work the same way. So I could do the same code for a vector. I could do the same code for a deck. I could do the same code for a list, and so on and so forth. So it makes it really simple to do plug and play combinations of containers and algorithms by using iterators as the way to do that. Okay, so that's what I wanted to cover today. What we will do tomorrow is we will keep marching down through our containers, and we'll talk about decks, which are double-ended queues, so they're a little bit more sophisticated than vectors. We're also going to talk about the list container, and very briefly about forward list. There's not much to say about forward list because it's just a singly linked list as opposed to a doubly linked list, but the operations are essentially the same, except you can't go backwards. And then we'll probably tomorrow also talk about some of the other container-like classes in the C++ standard library that have some STL-like properties, things like string, bit set, val array, and so on and so forth. So if there are no other questions, I will look forward to talking to you soon. Everything will be available, as always, on my YouTube channel very shortly. And thanks, you guys, so much for coming. Talk to you soon.